Thank you very much. I start by saying that I would have loved to get an ESI grant. I didn't, but don't worry, it's okay. But I got a big national grant, so I'm fine. I don't complain, absolutely. No, don't worry. So I start by thanking Laura, Vittoria, and Alexander to having invited me here to this very beautiful place. Actually, for me, it's the second time. Since the first time I was here, I was invited by Christoph Delago in 2008. Time flies. A workshop on rare events. So I'm back at the ESI Institute, and today I'm going to tell you about our results on discovering dynamic laws from observations. I start by presenting you the team I've been working with. So this, if the pointer works, does it? Yes. My very talented PhD students, my Spanish collaborators, and my collaborators at Columbia University, Padova, Erlangen, and Oxford. And this is the outline of my talk. I start by reminding you what active matter and active particles are, focusing on active Brownian particles, and how we, and many others, got inspired by soft matter in order to study the behavior of active Brownian particles, and our recent work on discovering dynamical laws from observations. So, as we learned in the last 20 years, active matter systems are made up of units that consume energy in order to perform an action. We saw yesterday from Daniela, Christina, and Angela, the actions can be different. I'll be only focusing on active particles that absorb energy from their surroundings or from an internal fuel and dissipate it while moving around. Active particles can be living, such as fish, starlings, and bacteria, or can be synthetic, such as active colloids. And we can mimic the behavior of active particles by means of computer simulations. Now I'm going to show you a few of the many models that have been developed in the last 20 years to study the collective behaviors of such systems, such as active Brownian particles, active aligning particles, or a model to mimic the behavior of bacteria, such as ensemble particles. Throughout the rest of my talk, I'll be only focusing on active Brownian particles. These are self-propelled Brownian particles. This is an example of a spherical self-propelled particles, and the equation of motion can be summarized in two dimensions in a translational and rotational equation of motion. We focus on the translational equation of motion, we forget about the red contribution. This is just the equation of motion of a Brownian colloid, plus a propelling force that tells us that the particles self-propel towards a given direction as long as it can, and at some point it changes its direction of motion and it propels in a different direction. This change of direction is governed by a rotational equation of motion that depends on the reorientation time tau r, that is inversely proportional to the rotational diffusion coefficient, that it tells us how long a particle performs a straight motion before changing its direction. Sorry. And we use an 8-dimensional number called Peclet number to quantify the amount of activity. So the Peclet number depends on the propelling speed of the particle times the reorientation time. Just to understand the meaning of this number, when the propelling speed is 0, a particle is passive, and we can tune the activity of a particle by tuning the Peclet number. You can already see a problem here, because VA is the propelling speed, tau r is the reorientation time, sigma is the size of the particle, but these two numbers we can tune the Peclet by changing either one number or the other. I'm going to show you soon that this is going to lead to different behaviors. And what about this contribution? Sorry, I have a bit of a cough. This is actually nothing but the interparticle interaction. So how can we tune this, the interaction between active Brownian particles? Coming from a soft matter background, we know that depending on the interparticle interactions, we do expect different phase behaviors. So can we learn from soft matter and use these interactions in active Brownian particles and learn what happens for these out of equilibrium systems? And this is what we have been doing in the last 15 years. So interactions can be isotropic or anisotropic. I'm only going to focus on isotropic interactions, and could be, for instance, attractive or repulsive. We learned 20 years ago by Henkel, Kerker, and co-workers that if we add to a colloidal suspensions polymers, polymers induce a depletion-like attraction between colloids, and eventually, by adding more and more polymers, the system undergoes a phase separation between a colloidal rich and a colloidal poor phase. That reminds a gas-liquid phase separation. What happens now if colloids are active? So in a suspension of self-propelled particles and polymers. This is the work we did back when I was in Edinburgh. When we studied a suspension of non-motile E. coli or motile E. coli in the presence of polymers. And increasing the polymer concentration, we observed the following. First of all, for us, the active particles were E. coli bacteria. And increasing the polymer concentrations, bacteria started aggregating, forming transient clusters. And we observed this by also mimicking their behavior with simulations of active Brownian dumbbells, where we mimic the depletion attraction with a short-range attraction. So these clusters not only form and break, but they also rotate. And the reason for their rotation was mainly the elongated shape of the bacteria. You have to imagine that when two bacteria come together, they stick, and due to the fact that they are elongated, they start rotating. And we observe this both in simulations and in experiments. Now, increasing even more the polymer concentrations, eventually we observe the phase separation between a bacteria-rich and a bacteria-poor phase, either when the E. coli was non-motile or when the E. coli was motile. However, when the bacteria were actually motile, so when particles were active, phase separation was taking place for much larger polymer concentration, meaning for stronger depletion attraction due to the fact that particles were active. These transient rotating clusters can be observed not only in 3 dimensions, but also in 2 dimensions. And again, I stress it once more, clusters rotate just because particles are elongated. Now, when particles are spherical, but there is an explicit attraction between active Brownian particles, particles can form clusters. They do not phase separate, but they just form clusters as long as there is a competition between the equilibrium, the active force. So when the attraction strength is as strong as the propulsion force, we do get a cluster formation, both in 2 and in 3 dimensions. Now, if we want to control the size of these clusters, again, learning from soft matter, we know that an interaction that is characterized by a short-range attraction and a long-range repulsion is what we need for micelle formation, so to control the cluster size. And indeed, what we did find was that by playing with these attractions, so a short-range attraction and a long-range repulsion, when particles were spherical, we did form a fluid of transient clusters. This is just a snapshot showing these fluids, where we could now control the cluster size. However, it was nice to see that when particles were elongated, we did form a crystal this time, because if you look at it, it looks like clusters seem to be located at a sort of with an hexagonal order. So we did see the formation of a crystal of spinning clusters. And what about when interactions are repulsive? As Mike Cates and Julien Taillet showed us 15 years ago, when increasing the particle concentration and the activity, a system of repulsive active Brownian particles undergoes a motility-induced phase separation. So the system phase separates into a dense here in yellow and a dilute here in purple region. And it is a very interesting effect because here there is no explicit attraction between particles. This phase separation is induced by particles motility. However, these phase boundaries are not well defined because, as I mentioned before, this Peclet number can be changed by either changing the reorientation time or changing the propulsion speed. And as you can see, this phase boundary moves because the system is not an equilibrium system. What happens now in experiments? So in experiments, many different groups observed that when dealing with synthetic active colloids, colloids can form these transient leading clusters. And it is interesting to stress, as already suggested yesterday by Danielle and Christina, that there are many different propulsion mechanisms to make active colloids in a lab. So you can have induced charge electrophoresis, or you can have catalytic or photocatalytic active colloids. And now the question for theorists and computer scientists is, how do I really try to understand these experiments? So if I want to claim that my computer simulations resemble experiments, what do I do? Can I really obtain forces directly from trajectories? I'm talking about trajectories because nowadays most experiments rely on confocal microscopy. So from an experimental point of view, we do know that particles' trajectories, but then our question was, can we really use this information to extract forces acting between synthetic active colloids? So we were inspired by the work of Kramer and co-workers, where they use deep learning with inductive biases to learn forces between. They are astrophysicists, so it's a completely different field. But the idea was to use deep learning, with inductive biases to learn forces, and that's what we actually did. So we built graph on neural networks that we called ActiveNet for a system of active particles, starting with inductive biases. So the first assumption is that particles' motion is Brownian. All particles are equivalent, and there are no many-body interactions. These are our starting assumptions. And we built a graph of two networks. Sorry, here you see one in pink and one in orange. So the orange network is described by an edge function. So it's a perceptron with 300 layers. And the input information are Ci, Cj, meaning all particles' positions or orientations of particles I and particles j. So the edge function, what it does, it takes pairs of particles and computes the excited or just distances between particles and sum them all up. And then we have the node function here in pink that takes as an input the output of the edge function and all this psi and all Ci, so all information for individual particles, and gives us the predicted velocity. So with these two, with the node function, we can predict the velocity of each particle. And knowing the velocity, what we do is we minimize the loss function computed as the norm one of the difference between the measured velocity and the predicted velocity. These allow us to compute not only the active force that is computed from the node function, setting the contribution from the edge function to 0, and the two body forces as the node function minus the active force. I'm stressing the fact that we are computing forces, not potential. So that's the reason why we can use this method for an out-of-equilibrium system such as suspension of active Brownian particles. Now, how do we know if the method works? We rely on computer simulations. With computer simulations, as you do understand, everything is trivial because I know exactly what's the interaction force and the propulsion force because these are the input of my numerical code. So I just hope that ActiveNet, that the graph on neural network, is going to give me the correct interaction force and active force, and luckily indeed it did. So these are the results we got for a system of active Brownian particles, where particles form living clusters, and the continuous line is the numerical simulation we get, the input of our simulations. The dashed line is the input of our simulation. The continuous line is what the graph neural network gets. The difference is only due to the fact that we simulated a smaller system. When dealing with a larger system, this difference is smoothed out. So we could, and these are just stressed the fact this is a force as a function of interparticle distances. We also simulated a system where particles were interacting by means of pure repulsive interactions, but undergoing a motility-induced phase separation. So as you can see, the graph neural network was recovering a WCA-like interaction. And we could also measure the compute and measure the active forces. Here you can barely distinguish between the dash and the continuous line. And just remind you that the dash line is what we input in our simulations, and the continuous line is what the graph neural network measures. Here, the active force is plotted as a function of the of the orientation, and as you can see, active forces are isotropic as one would expect. Are we using enough data for our graph neural network? We compute the mean absolute error for the active force and for the two-body force. Here, basically, the bluer the color, the smaller the error. Here, we are plotting the mean absolute error when we varied either the temperature of the number of frames, and actually, both for the active force and for the two-body force, our whatever we measured was somewhere here. So when dealing with repulsive or attractive forces, we were dealing with of the order of few hundred frames, each frame containing few thousand particles. And so when dealing with few hundred frames and few thousand particles, the mean active error, the mean absolute error is actually pretty small. And these numbers are the numbers experimentalists are dealing with. So an experimentalist can give you of the order of few hundred frames, and each frame can contain of the order of few thousand particles. So being reassured by our numerical test, we said, can we actually use this tool with experiments? And that's what we did in collaboration with Dirk Hartz. So Dirk gave us very beautiful trajectories of his experiments. As you can see, his experiments were electrophoretic Janus particles, so charge-induced electrophoretic active colloids. Each particle, you can clearly see it here. You can nicely see that Dirk was even able to distinguish the metal coating, so the metal cap with respect to the silica bit. So he could not only give us the particles' positions, but also the orientations. And so, answering to the question, can we obtain forces directly from trajectories? The answer is actually yes. And that's what we did. We used ActiveNet to learn active forces. Each line here corresponds to different electric field amplitudes and particles concentration. The largest forces corresponding to the largest electric field and the the lowest concentration. And our numerical estimations corresponded to the Dirk's experimental estimations of the active forces. Then we also proved that the active force was scaling with the amplitudes, the field amplitude square, as already suggested yesterday by Daniela. And we learned the two-body forces. And the two-body forces as a function of the interparticle distance showed us that particles interact repulsively with an exponential decay. And we could actually also characterize the prefactor and the exponent constant that defines a length scale of one particle's diameter. What we really liked was the fact that the graph neural network was also telling us when it failed, because actually, as you can see here, there are cases where the network is clearly giving a wrong answer. And this, we really loved it, because this is telling us that our initial assumption that interactions were only two bodies doesn't work here. But here is actually this value of the electric field and concentration corresponds to motility-induced phase-separated system, where we do know that many body effects might play a role. So that's why we liked this, our approach, because you can even learn when it's not correct to assume that interactions are only two bodies. So we started thinking, can we actually also learn the stochastic contribution? Because for now we have learned two-body interaction forces, we have learned one-body propelling force. Can we learn the stochastic contribution? We use computer simulations to demonstrate that this is indeed the case. So each particle's velocity consists of a deterministic part and a stochastic part. So given that these are Brownian dynamics, in practice, we measure the velocity by means of computing the position at times t plus delta t minus the position at previous time divided by delta t. And when comparing the measure to the ground truth velocity, the only difference is basically the stochastic contribution that is absent in the ground truth of velocity. What we then do is we compute the loss function, and the network works when we minimize the loss function. But if we actually explicitly write down the expression for the loss function, what we learned was that the loss function is nothing but the stochastic contribution of the velocity. So actually, the loss function is giving us the stochastic contribution of the velocity. So the loss function is the norm one of the velocity difference. If we explicitly write this down by just writing down the full expression for the velocity, the measured and the ground truth velocity, what we did find was that the loss function is square root of dt. So dt is what we were looking for. So the translational diffusion coefficient can be learned from the loss function. And we tested this by computing just for one of our numerical systems. So active Brownian particles are of a when particles interact repulsively. And I just stressed that this is a log-log scale. So when plotting the loss function as a function of this square root of 8 dt divided by the delta time. And what we did see was that when the number of frames was ridiculously small, even so, up to a given, and sorry, I just stress again that these are spanning many decades, okay? Up to of the order of 1, even using few frames was giving not such a bad answer. However, I mean, this is not the number of frames we deal with. Our usual data set relies on few thousand of frames, mixing between frames and particles. So we could actually go all the way down to a very small number. And down here, we have a numerical resolution problem. So we've estimated all coefficients of the equation of motion. And so we were wondering, can we actually use this method for passive particles? Can we learn torques? Can we, what happens if the dynamics is not Brownian? So ActiveNet, of course, can be used for passive particles. In that case, if I have a sphere, the rotation equation of motion is completely useless. So I'm just using the translational equation of motion. And if I consider repulsive passive spheres, what we tested for now, just in computer simulations, is that we recover the two-body repulsive interactions and that the active force is set to 0. Not set to 0, is measured as 0. Our goal is now, and we teamed up with Roald Dollens and Dirk for this, they're going to give us trajectories of hard spheres. We're going to plug in hard spheres and see whether hard spheres are really hard spheres or what they are. So passive hard spheres, normal hard spheres. And then can we learn torques? And of course the answer is yes. So we simulated chiral active Brownian particles. Now these are active Brownian particles characterized also by an active torque. And the only difference with respect to the previous formulation of the ActiveNet is just we need to add more information to the node function. So the information of the angular velocity. Having done so, we can compute the torque and from the node function get the predicted torque. And again, we can minimize the loss function this time of the angular velocity. And we're going to get we tested the method for different values of the active torque, and we always got this is a slope 1 line. So we recovered the measured torque. And so ActiveNet can be used not only to predict two-body forces, but also to predict active forces and active torques. And if the dynamics is not Brownian, we consider, for instance, the example of an underdamped Langevin dynamics, where now we have inertia, and we also have the dissipative force. And so, again, this time we're going to need to add more information to the node function, meaning the node function also needs to know the velocities because the node function is going to learn acceleration. And by minimizing the loss function of the acceleration, we can also compute the drag force. So from this, we can, how do we know whether we are doing things right? Again, we use computer simulations, and since we know the drag, the friction coefficient we are using in simulations, by comparing it with the drag force we get from ActiveNet, we can again compare the dashed line that is the input of our simulations with the continuous line, and we get a reasonable comparison. So ActiveNet can be also used to learn non-conservative forces. And our idea is just to suggest this graph neural network as a tool to infer interparticle interactions, non-conservative and active forces. And we are working nowadays with Lucio Isa and Max Paley to try to learn interactions and activity from their photocatalytic active colloids, and also with Jeremy Pallacci and with these chiral active particles, and with Erika Eise with her colloids trapped via an external laser. And with this, I want to thank you for your attention.